Hello children, welcome to this enrichment classes of the Public School Gumla. Today I am going to deal with a topic which is existence of limits. This topic requires a robust understanding on the graphs of various functions. So we'll first test whether limit exists or not, and we'll test it for some special functions, right? So let us proceed. For special functions, let us talk about the concept of existence of limit, right? As we know, when I draw a graph, suppose this is the graph, right? And I have a curve f of x, then suppose this point is x. In the neighborhood, if I take very close, actually this height itself, it is nothing but, look at this height is called limit. I repeat, suppose here I draw this one and this point is suppose a. This height will be representing limit x tends to a f of x. Clear? Now what happens for left hand limit and right hand limit? I will be testing that thing, right? And for suppose this is a, this point very close to a, this is called a minus, and this point is called a plus. That means this is the location of a minus and a plus. So this is called RHL, this height, right? And this height will be termed as LHL, right? RHL stands for left hand limit, sorry, RHL stands for right hand limit, and left hand limit is called LHL. Now we say limit exists. Suppose this is the limit concept, and limit exists if this height will be equivalent to this height, right? Then only I say that the function has a limit, right? So the various condition under which limit exists, I am noting it down. Remember children, limit of f of x at a point x equals to a exists if left hand limit it is equal to right hand limit. That means I should write limit x tends to a minus fx must be equal to limit x tends to a plus fx, right? So this is the basic condition under which the limit said to exist, right? So x tends to a minus and x tends to a plus, this is standing for LHL, okay, and this stands for RHL, right? Now what is the meaning of this? Let me show it graphically, right? Suppose I draw a graph like this. Clear? Yes, I have taken it like this. Now at this point, you see, at suppose my graph goes like this, right? And at this point it goes like this. Clear? Now suppose I say this point is a, so this height will be called as a minus, that is LHL, and this height will be called as a plus. Clear? So here you see, if I can judge, you see, this height is called LHL and this height is called RHL, and clearly here LHL is not equal to RHL, hence here the function is said to be having no limit. So limit doesn't exist, right? Now let me proceed to give another example where limit exists. Clear? Let me draw the graph. Yes, I draw it like this. Now here you see, students, Suppose I take this point as A, this height slightly left will be called as A minus and slightly right will be called as A plus. This height will be called as LHL and this height will be called as RHL. Now you can clearly see here that this height, this is the LHL and this is the RHL, they are same. So here LHL is equal to RHL, hence here I say limit exists. So this is the concept of our existence of limit, right? Now let me take a very small example, then I will plot the graph of special function to see whether their limit exists at particular points or not. Clear? So suppose I will ask you test the limit whether it exists or not. I will give you a question. Fx equals to 5x minus 4 when x lies between 0 and 1, and here 4x cube minus 3x when x lie between 1 to 2. Now you can see there is a point here in this question where the function is not properly defined. You see, when at 1 I say slightly less than 1, I get some other value of the function, and slightly greater than 1 I get some other values of x. Clear? So function, the value varies. This is for slightly greater than 1 and this is for slightly less than 1. So what should I do? I will test for 1. Clear? Now for that you draw a straight line and place x equals to 1. Now prior to 1 the function fx is defined as 5x minus 4, and after 1 the function fx is defined as 4x cube minus 3x. Clear? Now let me find LHL first. Clear? So here LHL, it is written like this: limit x tends to 1 minus fx. Then in the next step you remove plus or minus, right? So limit x tends to 1. Now in place of fx you choose that value of fx which is at the point 1 minus, right? So at 1 minus I can clearly see this is the value of the function which is defined. So I will write it as 5x minus 4. Now if I put 1, so 5 into 1 minus 4, which will be equal to 1. Now let me see what is the value of RHL in this condition, right? If I take RHL, this will be limit x tends to 1 plus fx, that is equal to limit x tends to 1, in place of fx I write 4x cube minus 3x. Now if I put 1, this is also 4 minus 3, which is 1. Now can you see LHL is equal to RHL, hence limit exists at 1. Clear? So I write at last like this: limit exists at x equals to 1. So this is how we test for LHL and RHL and simply say limit exists or not. But in the competitive exam you will not come across such functions, easy functions. They will be asking regarding special functions like greatest integer function or modulus function or reciprocal functions, right? So you see, now let me decide about modulus functions, right? Clear? Now first let me take the example of fx equals to mod x. Okay, now let me see what is the value of fx equals to mod x, right? Now for that what I'll do, you know the graph of mod x, right? In graph of mod x what I do is draw it like this. Clear? Next you draw it in this manner. Clear? Now in graph of mod x, what we will have is the graph goes like this. So this is the graph of fx, this is the graph of fx equals to mod x, right? F of x equals to mod x, right? So now you can see easily at all points the value is properly defined. So hence, even if I take very small point, whatever point I take, the slightly left and slightly right, if I take the point, the height will always remain the same. Hence the limit will always exist. Clear? So you see fx stands for two values. One is plus x or minus x. But if I take the function or graph of the function, you can see I can easily construct it, and at every point the left hand height will be equal to right hand height. Clear? So but how to test it? Suppose I will ask the limit exists or not at the point x equals to 0. So at that point, how to test it? Clear? So look at this. I will ask you if x equals to mod x at x equals to 0, suppose. Clear? So you find LHL. LHL will be limit x tends to 0 minus fx, which is equal to limit x tends to 0. In place of fx I place mod, but at 0 minus, children, mod x gives us two values, either plus x or minus x. So at negative value of x it gives minus x, and at positive value of x it gives plus x, right? So what I will do? So I will be writing at limit x tends to 0, this is minus x. Now minus of 0, it is equal to 0. Clear? Next, let me find RHL. RHL is limit x tends to 0 plus f of x, that is equal to limit x tends to 0 mod of x. This is limit x tends to 0. Now mod of x is again x, because at positive value mod of x gives us x and the value is 0. So here you can easily also see LHL equal to RHL, hence limit exists. Okay, so LHL equals to RHL, hence limit exists. So at every point you can test for modulus of x, limit exists at all points. Clear? Now look at this. Suppose I will take the example, very important one. Question is test whether limit exists or not. Limit x tends to 0, 1 divided by modulus of x. Now let me plot the graph of this function first. Clear? So for modulus of x, what I will do? 1 by modulus of x. This is simply not modulus of x. This is 1 by modulus of x. Clear? So for that, what I will have is like this, right? And here the graph will be like this, and here in this side the graph will be like this. Clear? Now you see, at 0, at all points it is special defined, but at 0 minus the height will be around like this, and at 0 plus the height will be around like this. So you can easily see, although the function is discontinuous, but at this point the height of the function remains almost the same. Clear? So for that I will be testing it, and I will see from the graph it is clear the limit exists at 0. Clear? So let me test it properly. Clear? Look at this. This is mod x. So I will find first LHL. Clear? LHL is limit x tends to 0 minus 1 by mod of x, that is limit x tends to 0 1 by minus x, that is equal to minus 1 by 0, which is infinity. Clear? Similarly, RHL is limit x tends to 0 plus 1 by mod of x, which is equal to limit x tends to 0, 1 by mod of x will give you x, so value is infinity. So here you can easily see your LHL is equal to RHL, right? This infinity is also equal to this infinity. So LHL is equal to RHL, hence limit exists. Clear? And it is equal to infinity. Clear? So this is the special behavior of modulus functions. Clear? Next, another function, let me take example. Suppose I will ask you limit x tends to 0, 1 by x. See the difference here. Okay, let me plot the graph of 1 by x first. Clear? This is the straight line, this is also the straight line. 1 by x is a hyperbolic curve, looks like this. Now you see, at 0 minus the height tends to this side, but at 0 plus the height tends to this side. So here this height is minus infinity and this height is plus infinity. So both are going in different directions. One tends to minus infinity and the other one tends to plus infinity. Hence clearly it is visible that limit doesn't exist. Clear? So why it doesn't exist? One will be plus infinity, another one will be minus infinity. Clear? So let us see it algebraically, right? So this is 1 by x, right? Now LHL, if I go, this is limit x tends to 0 minus 1 by x. So minus 1 by 0, which is minus infinity, and RHL will be limit x tends to 0 plus 1 by x. This is plus 1 by 0, which is equal to infinity. So clearly our LHL is not equal to the RHL. Therefore limit doesn't exist. Limit doesn't exist. Now why it existed in the previous one? Because of modulus. Here it was modulus, hence it was existing. But when it is modulus is removed, limit doesn't exist. I think it is clear to you. Now let me proceed towards the greatest integer functions. Clear? See here, if I go for greatest integer function, if I ask this one, question is limit x tends to, suppose 1, greatest integer of x. Now first let me draw the graph and explain it to you. Now greatest integer function graphs, they are step functions. This is suppose 0, 1, 2. Now for 0 to 1, whatever value, the graph will be shaped like this. Clear? This portion will be covered. For 1 to 2, if it is 1, whatever value between 1 to 2 I take, the graph will be looking like this. So at 1 you can easily see the height will be, left hand height is almost 0, not almost 0, it is 0, and right hand height, if I take this height, this will be almost 1. So that is why here clearly visible that left hand limit is not equal to the right hand limit, right? So hence limit doesn't exist at 1. So let me test it algebraically. Clear? If I go algebraically, then I will find LHL. LHL gives us, clear, LHL, it is equal to limit x tends to 1 minus greatest integer of x. So limit x tends to 1 minus, if I take the value, that is limit x tends to 1, and if I take the value, any value of x which is just slightly less than 1, so the value will be 0, right? So answer will be 0 in this case. But if I take RHL, limit x tends to 1 plus greatest integer of x, right? So this will be limit x tends to 1. Now x is slightly more than 1, because 1 plus means slightly more than 1. Suppose I ask what is the greatest integer of 1.2, it is 1. Similarly, greatest integer of 1.3 slightly more than 1, the value is 1, right? So here what I will put, for slightly less than 1 I will put slightly greater than 1 I will put this one as 1. Now you can see easily LHS is not equal to RHL. Clear? So LHL is not equal to RHL, hence limit doesn't exist. Is that clear? So like this we can test for various functions by taking whether limit exists or doesn't exist. Clear? So now today I will take up the last question regarding hyperbolic functions or exponential functions, and we'll see whether limit exists or doesn't exist, right? So look at this. Suppose about log functions, let me try, right? Log function means fx equals to log x, right? Fx equals to log x. Now if I plot the graph of log x, you have seen in your previous classes the graph of log x looks like this. It goes in this manner. Clear? So this is the graph of fx equals to log x. So you can easily see, wherever you see the curve is a continuous curve, and wherever you take the value will be given. So here fx equals to log x. Okay, this one was wrong, I think. Yes, because log is not defined in the left hand side of x. Clear? So how to plot the graph then? The graph will be looking like this. Clear? Look at this, like this. So this graph is fx equals to log x. So for whatever value in right hand side I take, I will always get the function to be limit exist. But before 0, this point is 0, before 0 the limit doesn't exist because the function is itself not defined. So here you can say that limit exists for all x belongs to R plus. R plus represents the set of positive real number. So limit exists for all x belongs to R plus. This is for log x. Now let us take for e to the power x. Clear? Suppose I take the example of fx equals to e to the power x. Clear? For e to the power x, the graph will be looking like this. This graph represents fx equals to e to the power x. So you can easily also see, wherever you take x, the value or the graph is a continuous graph. Can you see? This one becomes a continuous graph, right? So if it is a continuous graph, it is very much clear that limit exists at all points. So our conclusion should be limit exists at all points. All points means all real points. Clear? So I am giving the homework, you try to solve the questions. Your homework is plot the graph of all special functions and determine the points where limit doesn't exist. So this work is left as homework, and you try to solve this question. And if you are not remembering the graph of the function, you can take the help of NCERT book of standard 11. All the special functions graph is given over there, and you go through that thoroughly so that it will be easy for you to understand continuity, because after the existence of limit we are going to move to continuity. Okay students, that's all for today, and I hope that you will cover it very sincerely.